Good afternoon to all of you. So it is my pleasure to uh, give a lecture in this lecture series. Firstly, I thank Dr. Rajesh Kannan for inviting me to deliver this lecture. Of course, we will share the info. Are you able to see my screen now, Rajesh?
Yes, you are able to see.
Okay. So, this presentation title is Engine of Graphs and its Spectra. This content of this presentation is basically the part of the dissertation work done by my scholar, research scholar Gayatri. Now she is working as assistant professor in Katwa University. I think she also has joined this meeting. So in this presentation talk lecture, I'm going to give some like survey kind of thing about this product of various product of graphs and how these M-join of graphs and the generalization of all these kind of products. And we see this how the spectra of this type of product of graphs can be obtained. All these things. First, I start with the basic preliminaries. Some notations, well-known notations of graph theory. Usual the complete graphs, complete bipartite graph, cycle graph, path graph. These are all standard notations. And for complement of graphs, and NG of it, the set of all neighbors of your vertex in the graph. And some matrix notations that we used in this presentation. This J denotes the matrix n by m matrix, all of which entities are 1. And for a given matrix M, sigma m denotes its spectrum. And these we define these three classes of matrices. The first one is R n by m of S. This is the set of all matrices n by m matrices with entities from complex numbers. So that each row sum equal to S. Similarly, we define the next class of matrices, set of all such type of matrices having each column sum is a constant C. Then the set of all such matrices whose each row sum equal to S and column sum equal to C is denoted by RC of n by m of S comma C. Now, for this term, some standard matrices associated to graphs. I think most of you are familiar with these definitions. So I just produce the notations. So as usual, we denote the adjacency matrix of a graph by A of G and the vertex incidence matrix of a graph by B of G and degree matrix as D of G and Laplacian matrix as L of G, sinus Laplacian matrix as Q of G, and normalized Laplacian of G as L cap of G. Then the multi-set of eigenvalues of these matrices, these four type of matrices are respectively called as the A spectrum, L spectrum, and Q spectrum and L cap spectrum of the corresponding graph. And the characteristic polynomials of these four type of matrices are denoted respectively by Pg of x, Lg of x, Qg of x, L cap g of x. And we don't denote these three type of spectrum of the graph G with these kind of notations lambda i's, mu i's, and mu i's respectively. Then the definition for the generalized characteristic polynomial of the graph, which was introduced by Characterization, is defined as the polynomial pi g of x beta as the determinant of this matrix. Here, from this generalized characteristic polynomial, one can obtain the characteristic polynomial of adjacency matrix, Laplacian matrix, and signless Laplacian matrix. Okay. By suitably taking the values of beta and x. Here it is mentioned. Then something about co-spectral graphs. The notion of co-spectral graphs was initiated by the question which was raised by Van Dam and Hammers. He asked that which graphs are determined by their spectra. So people started finding several type of co-spectral graphs. Of course, the definition of co-spectral graph is simple. It is, two graphs are said to be co-spectral, and respectively L co-spectral, Q co-spectral, L caps co-spectral if they have the same A spectrum, respectively the three type of spectrums. They are specified. Because several spectral properties of graphs are same for the co-spectral graphs. So this shows the significance of constructing these co-spectral graphs, and consequently so several papers appeared in this direction for the construction of various type of co-spectral graphs. So in this direction, in 2010, Butler asked this question. That is there an example for two non-regular graphs which are simultaneously A co-spectral, L co-spectral, Q co-spectral, and L co-spectral? Of course, this question is an unsolved question, but now we have solved this. We have answered this question by providing one example. Because there was a partial answer to this question by some authors. They have obtained some example for graphs which are simultaneously A co-spectral, L co-spectral, and L caps co-spectral, but not Q co-spectral. Then now we come to the main topic of the graph operations. So the basic problem of spectral graph theory is to find the spectrum, that means various spectrum of given graphs. So in graph theory, there are several graph operations or graph products have been defined for various purposes. So in spectral graph theory point of view, suppose a given graph can be constructed using some graph operations. Then one can ask how far the spectrum of the given graph can be expressed in terms of the spectrum of the constituting graphs. So this is a very fundamental question. So in this direction, so a lot of research have been done for the past 25 years to find the spectrum of several spectrum of graphs obtained by several well-known graph operations such as union, complement, subdivision, Cartesian product, Kernighan product, NPS, Corona, join, deletion of vertex, insertion, deletion of edges, etc. Especially, so for the last 10 years, there are several graph operations have been defined as a variance of join of graphs and Corona of graphs, and several researchers have obtained the spectra, various spectra like adjacency, Laplacian, harmonics, and all these things for such type of variants of these kind of operations. So I think more than 50 different types of this Corona join type of graph operation that have been defined up now. So now what we are going to show is we are going to define a new type of some graph operation that is known as M join and M generalized Karana. And we will show that this type of graph operations generalize all these kind of operations within the literature, and we show that of course we have obtained the various spectra of these.
Rajkumar, you are not audible. Others, can you hear? Aniruddha, are you here? Can you hear? No, no. Okay, okay. I think he has some problem. Hello?
Rajesh, slide what was?
You have to reshare. Yes.
Oh, okay, 1 minute. I will share the slide. Is it okay now?
It's okay now. Yeah.
No.
Yes.
So, this graph overlay of two graphs generalizes the construction of a middle graph, total graph, and the quasi-total graphs. Its definition is the following. So take two graphs G and G days having same number of vertices with same vertex label in the V1 VN. Then the overlay of G and G days is a graph obtained by taking one copy of Q of G and join the vertices V and Vj of G if and only if V and Vj in G days are adjacent. So this is one nice construction made by Somar. Then
can you? Yes, yes.
What is Q of G?
Excuse me.
Yeah, what is Q of G in the last definition?
The Q of G is that I have mentioned already. Q graph. So these are the notations.
Can you explain what is a Q graph?
Huh?
What is a Q graph? Can you explain?
Q graph.
Yes.
Okay, then I think I have to repeat all these definitions. I hope that everyone is familiar with these definitions. That's why I have not introduced this definition. So if this is okay, I will repeat it. So this Q graph, or this is called middle graph of G, is the graph obtained by taking one copy of S of G. Take one copy of subdivision graph. Then join the new vertices which lie on the adjacent edges of G. Join the new vertices which lie in the adjacent edges of G. So for the construction of S of G, we introduce new vertices. Now we join the new vertices which are lies in the adjacent. This is the construction of Q of G. So Q graph. Then R of G, I think you know about this R of G, R graph.
No, I'm not familiar.
Yes, we are not familiar with this notation. Maybe we could spend some time over here to explain this terminology.
Okay. Then I just tell the definition of R graph. So I think I know subdivision graph of G. Subdivision graph, I think you are all familiar. Subdivision graph of G is the graph obtained by inserting a new vertex into every edge of that graph. And then R of G is the graph obtained by taking one copy of S of G and join two vertices of G if and only if they are adjacent in G. Okay. Then total graph. Total graph, I think this total graph is familiar to this is from old definition. Is a graph whose vertex set is all the vertices of G together with all the edges of G, and two vertices of P of G are adjacent if and only if the corresponding elements are adjacent or incident in G. That is, if the vertices means vertices should be adjacent, edges means edges should be adjacent. Then central graph is obtained by taking again S of G subdivision graph and join the vertices of P of G which are not adjacent in G. So this is the central graph. And quasi-total graph is again obtained by taking one copy of S of G, taking one copy of Q of G, then join the vertices of V of G which are not adjacent in G. Okay. Then duplicate graph, duplication graph of a graph is obtained by taking new vertices corresponding to each vertex. Taking new vertices corresponding to each vertex of G and join the new vertices to the vertices of G which are adjacent to the corresponding vertices in G of new, which are adjacent to the corresponding vertices in G of the new vertex and delete the edges of G. So this is known as duplication of graph. Okay, this is not familiar, then it's no problem. I will provide some more examples there. Within that graph structure, you can see the construction of R graph, Q graph, all these type of graphs. Okay, next thing is about the join of graphs. This is a well-known definition. I think it is familiar to all of you. So when two graphs G and H are given, then join of these two graphs is a graph obtained by taking one copy of G and H and join all the vertices of G to all the vertices in H. Now in the recent years there are several variants of join of graphs have been defined by several authors, and moreover they have obtained various spectra like adjacency Laplacian, signless Laplacian, normalized Laplacian spectra of these type of graphs on some class of graphs V and H. In some cases they have obtained with the spectra for general graphs also. So the list is given here from 2012 to 2018 onwards. So these variants are S vertex join, S edge join, H generalized join, H generalized join of graphs constrained by vertex subset, R vertex join, R edge join, VG join, subdivision vertex join, subdivision vertex edge join, Q double join, total double join, generalized subdivision vertex join. So many types of variants of join of graphs being defined. So So, but I am not including the definition of all these things here. But in the rest of the slides, in the join of graph slides, once again you will see the definition in another way. So that's why we are not repeating these definitions. Then another one well-known graph product is called corona of graphs, which is defined by Pritchett and Harari, and they have studied some of the graph theory properties of this graph. So this graph is constructed as follows. Take a graph G with n vertices and H be another graph. Then the corona of G and H is the graph obtained by taking one copy of G and n copies of H. G has n vertices means corresponding to each vertex we take one copy of H. And then join the ith vertex of G to all the vertices in the ith copy of H for each H. So such graph is known as corona of G and H. Of course, for the spectra of this type of graph operations concerned, in 2007, Barick and others determined the A spectrum and L spectrum of these graph operations for some particular cases of A's graph G and that copies H by taking regular graphs and some variants. Of course, later this graph was defined in 1970. Later, there are several variants of corona graphs also defined in the literature by many authors, and they have studied the various spectra of these graphs. So there is a large literature available for this kind of variants of corona graphs and its spectra. So still, it is a very active topic. This field. So from 2010 onwards, so some variants are edge corona, neighborhood corona, subdivision vertex corona, subdivision edge corona, subdivision vertex neighborhood corona, or vertex. So this basic methodology of constructing such type of things, for example, the edge corona definition is here usual corona of graphs. What we do is we take the base graph G and corresponding to each vertex we take one copy of H and we join the vertex of each vertex of G to the corresponding copy to all the vertices in the corresponding copy. Like that, for edge corona, what we do is we take a graph G. Suppose the number of edges of the graph is m, say m. Then we take m copies of a graph H. Take m copies of the graph H. That is corresponding to each edge of the graph G. We take one copy of H. Then join the n vertices of each edge of G to correspond to all the vertices of the corresponding copy of H. So the graph obtained by this kind of construction is known as the edge corona of G and H. A similar type of construction is made by several others. So this is the variance given here. So okay. So up to now, so these are all the variants of join of graphs and corona of graphs defined in the literature. So what we have did is we generalize all these notions, all these graph models by introducing this M join and M generalized corona. So now we start our work. We are going to present. I am going to present the work take by us. First, we are going to introduce special type of graph operation, which is known as H1, H2 merged subdivision graph of a graph. And of course, we will show later that this graph also is a particular case of this M-join of graphs, and we derive the spectrum of this graph from that M-join spectrum of the M-join graphs. The some part. So this is a ternary graph operation, which is defined as follows. So to define this graph, take a graph G with vertex set V of G, vertices V1, V3, N, and having a set E of G, E1, V3, N vertices and N edges. At H1 and H2 be two graphs having vertex set given here. The first graph is having n vertices and the second graph has m vertices. Then H1, H2 merged subdivision graph of G, that is denoted by this notation, and it is the graph obtained by taking one copy of S of G, subdivision graph of G, and joining the vertices Vi and Vj if and only if the vertices Ui and Uj are adjacent in H1 for I equal to 1 to n, and join the new vertices which lie on the edges Et and Es if and only if Wt and Ws are adjacent in H2 for each T and S. This is why we give the name merged subdivision, is that in one sense we take the graph S of G, subdivision graph of G, and we merge the graph H1 with the original vertices of the graph G, and we merge the graph H2 with the new vertices introduced in the graph S of G. So I will show an example, then we can understand this structure. Of course, we note the special case when this first graph H1 is totally disconnected graph, and the second graph also totally disconnected. It is SG of Kn bar and H, and SG of H and Kn bar. These two graphs we simply denote by SG of H and SG power of H respectively. This is an example. Here this is a graph G with vertices and edges are given here, and I will take a graph H1 with number of vertices same as the number of vertices of G, and H2 with number of vertices same as the number of edges of G. Now this is SG of H1 power H1 means now I merge the graph H1 with the vertices, original vertices of this graph G. Here look at this, V1 and V2 are adjacent in G. So we make a new edge in the SG of H1, this red colored edge, V1 and V2, new edge, we are adding a new edge in the SG of G. So to construct SG of G, first we subdivide this graph G. So this given here, SG of G. Then in the original vertices we merge this graph H1 here. Then SG of H2 is nothing but we are merging the graph H2 with the newly added vertices, that is like white color vertices. We merge these newly added vertices. Here we see this. Here E1 and E6, these two edges are adjacent in G. E1 and E2 are adjacent. So the corresponding vertices, newly added vertices are adjacent here. E1 and E2. So this is SG of H1, H2. H1, H2 merged subdivision graph of the graph. The complete structure is given. Here we merge the graph both H1 and H2 with subdivision graph. So this is construction of this graph structure. Here we notice that this definition generalizes many graph constructions. For example, here if we take this H1 to be Km bar and H2 to be Km bar, it is totally disconnected graphs, then we get the subdivision graph. Then this R of G, R graph of G is nothing but S of G and merging G, S of G power G. And the CP of G is S of G power G bar. And this overlay graph, also particular case of this construction, this is S of G of H and L of G. It is merging H and L of G, line graph of G. And Q graph of G is nothing but taking subdivision graph and merge this line graph, merge this line graph in the newly added vertices. And the total graph is nothing but S of G and L of G. And the quasi-total graphs, complete Q graph, all these things. So this construction generalizes several unary graph operations that are already available in this literature. So not only that, now we define some more interesting unary graph operations as a special case of this construction. So that is listed here. Take a graph G S2 with vertices V1, V2, Vn. Then the point complete subdivision graph of G is the graph obtained by taking one copy of S of G and joining all the vertices A and Vj of etc. That is, we are merging the complete graph in the original vertices of the graph G in S of G. So we call this point complete subdivision. That is, after subdividing the graph G, we are merging the complete graph with the original vertices of G. And Q complemented graph of G is a graph obtained by taking one copy of S of G and joining new vertices which lies on the non-adjacent vertices of G. So several type of graph operations which we have introduced here. Shortly denoting this definition is the following, so I am not going to read all these things, simply mentioning that the first graph operation, point complete subdivision graph of G is nothing but this isomorphicity S of G of A power Am. Second one, Q complemented graph of G is S of G merged with the new vertices L of G complemented. Third graph, total complemented graph of G is nothing but S of G of G and L of G bar. So like that, we have defined this type of graph operations. Quasi-total complemented graph, complete Q complemented graph, complete subdivision graph, complete R graph, complete central graph, fully completed subdivision graph. That is the construction of these graphs. Because the structure of these graphs for G equal to C4 are shown in the figures. There is a figure. The first one is take the cycle C4. It is the cycle. We have subdivided it. And now we merge the complete graph K4 with the original vertices. The red colored edges. The complete graph. So this is the point complete subdivision graph of C. Next one is the Q complemented graph of C4. Now subdivide this graph C4. Now with the newly introduced vertices, we merge the complement of the line graph. So this one. Next one is total complement. So these examples, these pictures, of course, when seen the published paper, that the references I will show at the end of this lecture. These are available. Because of time constraint, I just skip these things. Now, next thing we are going to do is finding the spectrum of these graph constructions. To obtain the spectra of these graphs, first we introduce this notion, is called the co-eigenvalues of matrices. Using this notion, we obtain the various spectra of these graphs. This is called co-eigenvalues of matrices. Suppose A1, A2, Am are square matrices of order n with real entries. Then the real numbers lambda 1 to lambda n, m are said to be co-eigenvalues of these matrices A1, A2, Am if there exists a vector x in
Yeah, I wrote him it as well. Hello. Disconnect ஆயிடுச்சுங்க. புரியலண்ணா. இப்போ ஒரு 2 மினிட்ஸ் கிட்ட ஆகுது. 2 மினிட்ஸ் ஆக போகுது. நான் மெசேஜ் பண்ணேன் அப்புறம் ஓகே ஓகேண்ணா. ஆஹா ஓகே ஓகே வாங்க. Yeah, he's joining in a minute. Yeah.
it okay now?
It's okay.
So where from I have to start? This one. Co-eigenvalues.
Yeah, that part we discussed. Maybe after the observation you can start.
Is co-eigenvalues is that presented already?
Yes.
Okay. So these are all some observations. It follows directly from the definition of co-eigenvalues. And for some class of graphs, we have obtained the co-eigenvalues of A of G and A of K, P, comma P. And G is spanning R regular subgraph of all these things. So these are all some progresses. Now we start to obtain the spectra of H1, H2, H3 subdivision graph of the graph. Here we notice that this adjacency matrix and Laplacian, signless Laplacian matrix of these graphs or of this particular form, the block matrices form. So it is given here. And then G is a regular graph and each H is RI regular. Then L cap of normalized Laplacian matrix of this graph is represented in this particular form. Now, to find the spectra of these matrices, we first prove this proposition. Of course, I just state the result only. I am not showing the proofs because it will be very lengthy. I just summarize the results only. So this result is if A is a matrix, n by n matrix, and P is a matrix in this class, then the characteristic polynomial of this particular block matrix is given by this equation. Moreover, if A and B transpose commutes with each other and n greater than or equal to n, then the spectrum of this matrix contains these values as the eigenvalues, where this lambda I of A, lambda I of B transpose are co-eigenvalues of A and B transpose. It is a result for this type of matrices. Using this result, now we obtain the spectra, various spectra of this H1, H2, H3 subdivision graph of G. When G is regular with n matrices and n edges, and HI also RI regular graph, where H1 is a graph having n matrices which commutes with G. Of course, H1 commutes with G means two graphs are said to commute if the corresponding adjacency matrix commutes with each other. And H2 is any graph from these four type of graphs. Then we obtain the A spectrum, L spectrum, Q spectrum, LK spectrum of this graph as follows, where the values of alpha I, beta I, gamma I, mu I are given here for each cases, for each of the cases, A spectrum, L spectrum, Q spectrum, we have provided the values for these alpha is, beta is, etc. So, and these values T1, T2, T3 mentioned here, and this can be obtained from this table A of G. This table you can obtain the value of T1, T2 here. For example, A of G means here T1 is minus R and T2 is 0, T3 is 1. This will give you corresponding values. And some more results in this direction. MG is R regular graph and HA is R regular, and H1 is a graph from these four type of graphs, and H2 is one of these graphs among these four type of graphs. Then we obtain the A spectrum, L spectrum, Q spectrum, all these four type of spectrum. And we obtain by taking beta values in the corollary, substituting the values in the corollary, and the S1, S2 values are given here. And as one more corollary of these results, we have proved that if G and G rays are regular co-spectral graphs, then U of G and U of G rays are simultaneously A co-spectral, L co-spectral, Q co-spectral, L cap co-spectral. For each U belongs to U1. Of course, this U1 is nothing but this first. So here is the notation. Here U1 denotes the collection of all in definition 2.2. Together with the subdivision graph, R graph, Q graph, total graph, central graph, quasi-total, complete graph. So this class of graph operation we denote by script U1. So this type of. So this result says that if G and G rays are regular co-spectral, then if you take any unary operation from this class U1, then the corresponding graph U of G and U of G rays are simultaneously satisfying these four type of co-spectral. So this provides an example for question raised by Butler. So this gives an affirmative answer to the question raised by Butler. Now we vary the base graph. In particular, we take complete graph, totally disconnected graph, complete bipartite graph, and we obtain the spectra of H1 H2 merged subdivision graph. Then we take the special graph. So these are some results. This is a corollary of the previous results. This is H1 H2 merged subdivision graph of star graph, and then H1 H2 merged subdivision graph of the path graph. Then for the Q complemented graph, we have then complete subdivision graph, all these results. So this is some results about this merged subdivision graphs. Now we come for the main section. This is the M join of graphs. Of course, this type of join of graphs was introduced by Anthony in 1969. He introduced this generalization of join of two graphs and studied some graph theoretic properties of these kind of graphs. So the definition is as follows. So for given two graphs G and H and given a binary operation pi on G cross H, then the pi graph of G and H is the graph whose vertex set is vertex set of G union vertex set of H, and the edge set is edge set of G union edge set of H together with pi. So this is now is defined it as pi graph of G and H. Notice that this binary operation, binary relation pi can be viewed as a matrix M equal to Mij, where its ij, pnt, Mij equal to 1 or 0, according as the ith vertex of G and the jth vertex of G are related or not. If the ith vertex of G and the jth vertex of H are related in the binary relation, and the corresponding entry of the matrix will be 1. Otherwise, it will be 0. So we can view this binary operation as a matrix form. So we can restate this definition pie graph of G and H in terms of matrix notation as follows. It is, take two graph G and H with vertex set V of G as U1 V2 Vn and vertex set of H as V1 V2 Vm, and take a matrix M as a 0, 1 matrix of size n by m, because G has number of vertices n, H has number of vertices m. So we take a n by m matrix with 0, 1 elements, and then the m join of G and H is the graph obtained, was denoted by this particular notation, is the graph obtained by taking one copy of G and H and joining the vertices ui and vj if and only ijth entry of n is 1 for I equal to 20. If and only. So if and only it means if the ijth entry of the matrix is 1, we join the corresponding vertex ui and vj. Otherwise, we do not join the vertices ui and vj. If the ijth entry is 0, we do not join it. So this is a formulation of this pie graph of G in terms of matrix notation. For example, consider the graph G and H given here. These two graphs, and let pi denote to be the particular binary operation, the binary relation given here. Then we can write this binary relation as a matrix form like this, capital M. So it is a pi by 4 matrix, because now G has 5 vertices, H has 4 vertices, so correspondingly this matrix is a pi by 4 matrix. Now how to join this, how to form the M join of G and H. Now look at this matrix. For example, here the first entry is 0. That means here you take the first entry U1 and V1. U1 and E1. V1. Here the 1 entry is 0. So we do not join V1 and U1 and V1 in the M join graph. And then 2 entry is 1 here. So we can join the vertex U2 and vertex V1. U2 is here and V1. So this edge U2 and V1. Similarly, for example here 4, 2 entry is 1. So we join U4 and V2. U4 and V2 this. Similarly for the other entries. So the corresponding graph is shown in figure. This is the M join of G and H. Of course, when we take capital M to be the matrix having all ones, then this will be the usual join of G and H. Of course, we will define various variants of join of these ones also. Now we extend this definition for K graphs by using a sequence of matrices as follows. Now let Hk equal to be a sequence of graphs H1 S2 Hk. We take a K graphs H1 S2 Hk with vertex number of vertices in each H is ni, and script M to be the particular sequence of matrices Mij. Each one is a 0, 1 matrix of size ni by mj. Then the M join of the graphs in Hk denoted by this notation. It is the union of the M join the union of Hi, Mij joined with Hg. Like the union of this. That is, we take this graph H1 H2 Hk. Then for each pair of graphs, we introduce one matrix Mij. Now we join the graphs Hi and Hj with respect to this Mij matrix and take the union of all these graphs. Then we will get the M join of these graphs H1, H2, H3. Here notice that this particular type of join of graphs has a special property that any graph can be viewed as a M join of these graphs. This is an important one. Because given a graph operation, suppose we have a graph, if one can ask whether this graph can be obtained from a graph operation of some graphs, then it may not be possible for some graph operation. But this graph has the property, this operation has the property that any graph can be expressed in terms of M join of some suitable graphs. So the construction is given here. Suppose G is a given graph, then it can be viewed as a M join of Hk for some suitable matrix M, matrices Mij and class of graphs. Where we take the Hk as H1, H2, Hk is a sequence of k pairwise vertex disjoint induced subgraphs of G with vertices Vi, vertex set of Hi is this one for each I, thus that the union of these vertices of Hi is equal to vertex set of G. And take script M to be the sequence of these matrices of size Ni by Nj with the entities of matrices defined as follows. The ijth R comma St entry of the ijth matrix is 1 if UIR and UJS are adjacent to G, and take 0 otherwise for each R and S. Then this particular join M join of Hk will produce the graph given graph. So as a consequence, this M join of graphs from this M join of graphs implies all the variants of join of graphs depending on each other. Of course, before going to see the definitions, we provide some examples. Let H1 and H2 be a graph shown in figure, these three graphs, take the graphs. And we take these three matrices M12, M13, M14, M23. Then let H3 script H3 is a collection of these three matrices. Script M is these three, taking these three matrices. Then M join of H3 is shown in this particular figure. So this H1 is there here, H1, H2. For H1 and H2, we join H1 and H2 using the matrix M12. Then H1 and H3, we join it using M13. H2 and H3, we join using M23. So we produce this. Of course, not necessary to take all these three matrices. If we take only first two matrices, then the third corresponding the blue color edges will not appear. So this is now, as a particular case of this M join of two graphs, we obtain several existing unary graph operation as well as several new unary graph operations which are listed in this paper. This take a graph G and take a graph H to be totally disconnected graph, and the joining matrices as identity matrix. That is, join each vertex of G to the corresponding isolated vertex. That graph is known as C graph of G, that is already defined in the literature. And take G and G itself, take two copies of G and join them using the identity matrix. That is, join each vertex of G to the corresponding vertex, same vertex available in the second copy. So that type of join will produce the mirror graph of G. Then G and G bar and join it with using the matrix I and identity matrix, that we will call it as V complemented neighborhood of G. That is, we take one copy as G, another one copy as G complement. Then using the matrix identity matrix, we join these two graphs. V complemented neighborhood. Similarly, we define all these type of matrices using adjacency matrix. This one is the 13th one is take G and Kn bar, then take the adjacency matrix of G as the joining matrix. This type of graph is known as N graph of G, then N neighborhood graph of G. So all the variants of join graphs will be here.
Rajkumar, I'm sorry to interrupt.
Yes.
Yeah, it's almost time.
Huh?
The time is up almost. It crossed. It crossed 5 o'clock.
Okay.
Yeah.
5 o'clock. Okay, I will just briefly explain the content of this join of graph chapter.
Okay.
So these are all several variants of join of graphs. Then what we did is we take this set of all unary graph operations mentioned in this table 6 and 7 respectively as U2 and U3. Then we take script U as the union of all these three type of unions, three classes U1, U2, U3. And we denote the new vertices of U of G as I of G for each U belongs to. Then we use some notations corresponding to each of the unary operations in U1 and U of G of particular form. This H1 join H2 with respect to B of G, where H1 is this type of graphs, H2 is this type of graphs. Then using the table 4, we can write A of H1 and A of H2 in this form, and we call that corresponding numbers, coefficients, sequences as the scalars corresponding to U in U1, or the sequence of scalars corresponding to A of U of G for each U belongs to U. Similarly for the other type of class of operations. So these are all some notations. Then what we did is we obtained the A spectrum, L spectrum, T spectrum of these several unary graph operations defined in this table. So these are all some results about the spectra. Then the main result is this one, the spectra of M join of graphs. Here we notice that the spectra of this M join of graphs, adjacency spectra is of this particular form, block matrix form. Now for the spectra of this M join of graphs function, the main result we obtained is theorem 3.2. That is, if H equal to H1 H2 H3 is a sequence of average commuting regular graphs, each having n graphs, and M is a sequence of these matrices which are pairwise commuting matrices such that each mi belongs to this class and commutes with this. Then A spectrum, L spectrum, Q spectrum of M join of HK are given by this one summation T equal to 1 T and sigma of A of T, where A of T is this matrix and the values are given here. So this is a major result, and from this result as a special case, we deduce several results on the M join of graphs, spectra of M join of graphs. This is one corollary about this one, and we have some more variants of join of graphs also we will define by taking a special type of matrices Mij. So these are all some variants of join of graphs constructed as a particular case of M join of graphs. So these are some examples, and we have proved some results on the spectra of this special type of graphs also, M join. And some more new variants of M join of using the unary operation that we have already defined. These are all some more new variants. Some examples and the corresponding results on the spectra of these graphs. This is given here. And of course, we have obtained several co-spectral graphs using these results. So this is the generalization of H1 H2 matrix subdivision graph. So we define 4 type of new family of join of graphs, in which this H1 H2 matrix subdivision graph is a particular family. These are also a special type of join of graph. Maybe you can see in that particular paper, quadruple join, all these things. So the main thing is that as a special case of our results, we have derived several results which are already existing in the literature. For example, taking these values, we can obtain the H generalized join, S vertex join, S join, R vertex join, etc. All these things. And so the spectral existing variants of join of graphs. So these results we have derived from our results by taking the particular values of the spectra of the results which we have obtained. So this is the main result. Here we will show this theorem, this kind of theorem, several theorems on R vertex join, R edge join, subdivision vertex join, subdivision vertex edge join. All these results on A spectrum, L spectrum of these results proved in the literature can be derived from the results proved in these pieces. So this is the thing. One more thing is we have generalized the notion of Karnaugh graph. This is known as M generalized Karnaugh graph. This is given here. And because of time constraint, I stop here. And I will show some references from that you can get the contents of these slides. This M join of graphs related results were available in this paper. It is published already. And H1 H2 matrix subdivision results are available here. And the generalized Karnaugh graphs constrained by vertex subsets also published upon. And for the case of M generalized Karnaugh graphs, this and this M comma M generalized Karnaugh is also a generalization of this one. So what we have finally with this this M join and M current of graphs, we have defined, generalized all the graph operation defined up to now as a variance of join of graphs and current of graphs, and the results of on the spectra of graphs we have obtained. From that results we can deduce all these spectra of results. So this is the main contribution of this research. And these are some of the references. So if you have any questions, you can ask.
Okay, yeah. Thank you, Rajkumar, for the interesting talk. Yeah. Audience, if you have any question, you can ask now. Okay.
Sir, is there any characterization has been done using this operation?
Is there any
Characterization of graphs.
characterization of graphs?
Yes, sir.
No, usually what we have did is we have obtained the spectra of the graphs obtained by these graph operation, M join, M current, all these things. But one thing we have already known in spectral theory is once we know the spectra of graph, then we can tell several information, structural information of the graphs. Okay, so that is a general thing. So here from this graph operation, from these results means so we have obtained the spectra of this graphs. So from this information, once again we use that results, known results, it is already available. From this one can obtain the information of the graphs. So the main aim is to obtain the spectra of the graphs. What is the aim of spectral graph theory? So once we know the spectra of the graphs, then from the spectra of the graphs we can tell the information about the graphs. That's what we will do.
Okay, I think she's asking, you are giving construction of co-spectral graphs using the M joins. There is a counterpart, it's called graphs determined by the spectrum. So,
Graphs?
determined by the spectrum. So, can you construct such type of graphs using this technique? I think that maybe she's asking. Characterization graphs.
Graphs determined by
the spectrum.
So what you are asking is, suppose we know the spectrum of the graph. From that, can we give some which type of graph operation produce that type of spectrum? You are asking. So what you are asking, I am not getting.
Okay.
Graphs determined by spectrum means, suppose we know the spectrum. So which are all the graphs having this type of spectrum? So classify all the graphs having this type of spectrum. This is the problem of graphs determined by spectrum. Now what we have did is we have defined several graph operations and we have defined the graphs.
Okay.
Maybe this question can be considered like this. Suppose if we know the spectrum, then what type, this may be a special case, what type of M generalized, that is the M join of graph operation, will produce this type of spectrum? Are you asking this type of question? Is that correct?
No. So given a graph, given as when the graph is determined by spectrum, like that's the only graph which is having this spectrum. Can you construct? Can we construct those type of graphs using these M joins?
No. Actually, The graphs determined by spectrum means once the graph is known, so once the spectrum is given, so what are all the graphs which can be, what are all the graphs having this type of spectrum? This is finding all the graphs having this spectrum is one problem. So if there is a unique graph, if there is a unique graph having this spectrum, then that graph is determined, exactly determined to this spectrum.
Yes, yes.
Suppose if there is a class of graphs, then of course we cannot tell this is the only graph. There are some class of graphs having this one. But what we have did is graph operations on graph, then we obtain the spectra. Then from this, we don't think there is a relation.
Or maybe we can ask like this. You start with a graph which is determined by its spectrum. You take the subdivision of that graph, whether the subdivision also will be determined by its spectrum. You have introduced many unary graphs, unary operations. So you start with the graph which is determined by its spectrum. You apply any of the unary operations on this graph. Whether the resultant graph will it be again determined by its spectrum. So I think that's I don't know anybody consider this.
What is it? We start with a graph
which is determined by its spectrum.
Okay.
Okay. Now you apply that unary operations like subdivision, or you have given lot of unary operations.
Okay.
Will you get again a graph determined by its spectrum after applying this unary operation?
No.
Maybe it might be an easy question.
This is a new problem. This we are not focused. So what type of graphs? That means we have to focus on graph operations. I think of course this type of problem we are not focused yet.
Okay.
So this is entirely different one. But we would see whether how much this is possible.
Okay.
But we have to properly reformulate this question.
Okay.
Properly.
Hello, sir. I have a question.
Yeah.
Sir, I've seen a slide saying that the Butler proposed a question to find out the graphs which are simultaneously co-spectral.
Okay.
Which paper is that, sir?
Yeah, that paper I have mentioned here.
Sir, can we proceed by taking, suppose I take two graphs co-spectral, and taking two co-spectral graphs, I may try to construct the co-spectral pairs of like L co-spectral and Q co-spectral. Is that the problem, or should we take two different different graphs so that we need to construct co-spectral pairs of L and Q?
This is a good question. Actually, there are several papers in literature. They have what they have do is they construct co-spectral graphs by taking a co-spectral graph. From that co-spectral graph, they have constructed several co-spectral graphs. Some construction are there, but there is no general construction. Each paper describes some different constructions. So there is no general method to construct this type of problem.
I think if we can take join of two graphs, that may be possible, sir.
Join of two graphs?
Join of two graphs, just general join, not like URM join.
General join means that
every vertex is joined to every other vertex in the other graph.
Actually, what we have proved is that graph construction we have made provides graphs which are simultaneously A co-spectral, L co-spectral, and of course that four type of satisfies four type of co-spectral.
Yes, sir.
Of course, in that class there is what you have did, what you are telling. That class also one of the member I think.
That is also one of the member of your joint operations. Very particular case.
Very particular. But what we have obtained is very large class of graphs having this kind of property. Not only a single one, but a large class of graphs.
Okay, sir. Okay, sir. Shall I mail you, sir, to send that paper regarding the Butler paper, sir?
The Butler paper, I can give you a reference. It is already available. Of course, that you can see a reference from our paper that I have mentioned. The construction of engine of graphs paper.
Okay, sir. Okay, then I will find that.
I have mentioned that reference. So
yes, sir. Yes, I will find there, sir.
Okay.
Thank you, sir.
Okay.
Okay. Yeah, there are no other question. Thank you very much for that.
Okay.
Okay.
Thank you all for